And we're moving on to Chris Lovell. And Chris will tell us about passive galaxies in the ER. So, yeah, take it away.
Thanks, Ramil. And yeah, thanks to the SOC for having me on here. So I'm going to talk a bit more about flares again. So thanks to Will for giving a nice introduction to the project. I'm a postdoc at the University of Hertfordshire, working with Jim Geach. This is some work I've been doing since my PhD at Sussex with Peter and Stephen, as well as some of their students, Ashwin, Will, Demetrios, and Yusi, and also thanks out to the wider EU collaboration as well. So I'm going to talk a bit about passive galaxies at high redshift. So we heard a little bit about this on Monday with reference to some of the JWST programs. But so far from HST kind of programs, there's been evidence for passive galaxies out to about redshifts of 5. So this has been seen in a number of different programs. These have been selected both through SED modeling and also through kind of color selection diagrams. And you kind of see this evolution in the number density increasing with decreasing redshift to the present day. Compared to models, so some of the kind of state-of-the-art hydrodynamic models, there are actually quite significant variation between some of the model predictions. So these galaxies actually represent a kind of unique laboratory for exploring differences in feedback prescriptions in some of these models. So one of the questions that kind of comes to me when I see this is when and where do these very first passive galaxies emerge? Is this at redshift 5, or do we see passive galaxies at even earlier epochs? And obviously that would be of interest for some of these web programs that are actually going to be able to go a lot deeper in current observations. And what drives passivity during this kind of epoch? What causes a galaxy at these very early times when there's kind of abundant cold gas available to become passive? So that's kind of the motivation for some of this work. So as Will's already explained, flares is a series of 40 zoom simulations using the Eagle codes. This is full hydrodynamics. Each one of these is kind of a sphere, radius 20 co-moving megaparsecs, all selected from this large 3.2 gigaparsec cubes that matter only box. And we select a range of overdensities. So we've got these very overdense kind of protocluster regions. So these typically will evolve into clusters in the present day. So they're very overdense even at high redshifts. And it's in these environments that we perhaps expect to see more massive galaxies and perhaps more passive galaxies as well. So in the fiducial kind of periodic Eagle volume, it's about 100 megaparsecs on the sides. It's actually about 10 to the 4 times smaller than our parent box. So this kind of limits the different environments that you can sample in there. So flares is kind of a unique approach for studying these very overdense environments. So some early results kind of put on the archive last year, but it's just been accepted early this year, looking at kind of typical distribution functions, so the galaxy stellar mass function and star forming sequence and the star formation rate distribution function. So we see pretty good agreement with observational constraints in all 3 of these. And particularly with flares, we're able to extend the galaxy stellar mass function up to much higher masses and also produce much larger numbers of these very massive galaxies. So for this project, we were interested in passive galaxies. There's a number of different ways to select these, as we saw in the observational approaches. So we kind of experimented with all 3. So there's the specific star formation rate, so just a fixed threshold. You can also calculate the star forming sequence and then some distance away from that, which is shown by the kind of blue lines on here. Both of these are quite sensitive to the aperture with which you measure the specific star formation rate in the simulation. So in the Merlin and Santini papers recently, they actually state that, yeah, this aperture is incredibly important. So if you include larger areas, you may include kind of residual star formation on the outskirts, which then pushes your galaxy above your passivity threshold. So they use a definition of 4 times the half mass radius within which they calculate the mass and SFR. We use a similar definition here, but it's worth noting that some of these definitions are quite sensitive. And then we also looked at these kind of color selections as well. So these are obviously slightly inaccessible at redshifts greater than 5 at the moment. But using BPAS as an SPS model, so this is binary population synthesis, and then Ashwin's 2021 line of sight dust model as well. So presented that in a paper recently. He's actually going to talk a bit later about some dust radiative transfer predictions for flares. But these predictions are just using this line of sight model. We can calculate color selections, and we found that basically none of them sit within your typical Muzzin 2013 UVJ selection criteria. So we've actually defined kind of new selection criteria for these galaxies. If you wanted to select passive galaxies at redshifts 5 or above, for example. So the rest of the talk, I'm going to kind of concentrate on the specific star formation rate, just because it's a little bit easier, but we'll present those results in future work. So this is kind of one of the main results here is the evolution in number densities of these passive galaxies. So this is similar to the plot I showed before, comparing the different models. So the observational constraints here are shown in gray. The Eagle predictions from the periodic volumes up to redshift 5, slightly up to redshift 6, are shown in red. And then the flares predictions, which go out to redshifts of 7 or 8, are shown in blue. So this kind of neatly kind of extends the predictions from the periodic volumes. You can see it kind of matches up remarkably well. So this is using the weighting scheme from each of our Zoom simulations. So we have to weight the contribution from each overdense region or underdense region. And this seems to work remarkably well to agree with the periodic sims. And as far as I'm aware, these are the first predictions for these kind of passive galaxy number densities at these very, very high redshifts, at least from high resolution hydro simulations. So using the SPS and bus modeling from Ashwin's work, we can predict surface densities of these things and make predictions for JWST. So on the left, basically predict the number of objects per square degree at different redshifts, and for different kind of stellar mass cuts as well. Able to extend it again into the redshift greater than 5 regime. I've just noticed about 2 minutes before this talk, the numbers on the y-axis for this plot on the right are wrong, but there's just a normalization error there. But these are essentially predictions for different F150W cuts from JWST and the kind of detectability of different passive galaxies. And these are for all galaxies above a mass of 10 to the 9 M solar. So we're working on predictions, kind of tailored predictions for some of the Cycle 1 programs now. So looking at kind of the intrinsic properties of these passive galaxies, they tend to be kind of centrals. They kind of populate the main kind of plot here is the one in the middle at the top here, populate the kind of upper part of this black hole stellar mass relation. So their black hole mass at fixed stellar mass is high compared to the majority of the population. 50% of the stellar mass, we define that as the formation time. We find that most of these things form between redshift 6 to 8. So those passive galaxies found at redshift 5. So they've formed within the last few 100 mega years. But there are a number of galaxies with kind of similar mass black holes that are not quiescent. So they're not a complete sample of black holes. So what's actually causing the quenching? So we've done a little bit of digging into this. So each of these panels here shows an individual galaxy at redshift 5 that's passive, and the blue line essentially shows the star formation history for that galaxy. The green line shows the assembly of the black hole, so the mass assembly of that black hole, and then the orange bars here are essentially when that black hole is accreting. And so hopefully, the clear thing from this should be that there's a strong correlation between the black hole assembly and the decrease in the star formation rate. So essentially, as soon as the black hole turns on in the simulation, star formation is pretty rapidly quenched. And there's a few galaxies, for example, there's one in the bottom left where it remains passive for a few hundred mega years after that kind of AGN quenching event. So the AGN kicks in at around redshift 8 to 7, and despite little further growth in the AGN, it's actually efficiently stopped star formation in that galaxy for a reasonably long time afterwards. So this is kind of the first step with this. We're using Mega, which is a kind of tree-based or graph-based, structure finder that Will's developed to look at the kind of merger history of these objects and see whether the rapid assembly of the black hole is correlated with any merger activity. But as a kind of first test, we ran one of our regions with the AGN kind of turned off, and kind of clear point with this on the left is that you don't see any passive galaxies in that kind of no AGN run. So it's clearly AGN that are causing passivity in these very high redshift galaxies. You might note that some of these galaxies are actually quite relatively low mass for that to be the case, but we noted in the first paper that the kind of characteristic mass in which the AGN turns on is actually a lot lower at higher redshifts. So there's still an opportunity for AGN to switch on in these lower mass objects. So another thing we're looking at the moment is so we can see that a number of these objects in terms of their accretion rates, looking at their bolometric AGN luminosities, are very bright objects at redshift 6 or redshift 7. So the question is, are these very bright objects detected as AGN at these redshifts? Do they evolve into passive galaxies, and what's the fraction of them that do? So that's something that we're looking at in detail now. So I will finish up there. So just summarize some of the passive galaxy populations in flares. These will be accessible to JWST, see as well in larger numbers, probably with Euclid and Roman. We're making predictions for that. Passive galaxies at Z equals 5 tend to form at least 50% of their stellar mass between redshift 6 and 8. And then the kind of passivity is driven by very early AGN feedback. As mentioned, it's a kind of work in progress. I'm hoping to share something on the archive soon, but I'd be interested to hear anybody's comments or questions. Thank you very much for listening.
All right. Yeah, thanks, Chris. Really interesting stuff. So, yeah, we have a couple of minutes for questions. I guess there's already one on the slide.
Yep. So the question is, do you also study the mass assembly history of these passive galaxies down to low redshift, for example, to determine the existence of a halo galaxy assembly bias?
Yeah, so it's a great question. So one of the drawbacks of our approach with flares is that we only run these regions down to redshift 4.7. So unfortunately, we can't follow these objects forward in time. We have talked about picking a few regions and running these lower to see what their kind of descendants look like. This gets complicated by how we weight the different regions. If you're interested in the statistics of the descendants, for example, but yeah, it's something that we've spoken about, but yeah, it's not trivial to do with the flare simulations. Whereas something like even with the periodic ones, you obviously can do that, but then you're limited by not being able to predict that many passive objects at redshifts 5 and above.
You might have answered part of the question, but can you associate early time passive population with a certain low redshift population?
Okay, so one thing I didn't mention, I guess, is what's called the cluster eagle simulations. So these are what the name says on the tin, really. They are simulations of clusters at redshift 0. And they do have some high redshift snapshots. So these are obviously going to, for the most massive ones, going to trace these kind of protocluster environments that match some of the some of the regions we see in flares. So one thing we could do is look at some of the passive objects in those high redshift snapshots. Now, obviously, they will most likely end up as clusters in their descendants. So I'm not sure. Yeah. You're limited to make any kind of statistical inferences with that because it's not a statistically sampled population. They're just selected a range of clusters at redshift 0, different masses. So yeah, difficult, I'm afraid.
Maybe one more question.
Sure, let's ask one more. Have you looked into what differentiates galaxies that are quenched by early AGN feedback from those that are not quenched?
Yes, so one of the things, again, I mentioned at the end is looking at this kind of AGN volumetric luminosity function and seeing which of these galaxies are quenched or not. But yeah, we've also looked at things like the gas masses, the cold gas masses in these objects, whether they've had mergers, etc. I unfortunately don't have a nice statistical conclusion for you, but we've looked at a few different avenues for sure. And yeah, because of the way that flares is built, we can kind of compare that to the overall population, at least at that redshift.
Cool. There are more questions in the Slack, so maybe you can just continue the conversations on those there. Great talk again. Thanks.